Hello student and welcome to this lecture about percent composition. Percent composition is the percent by mass of each element in a given compound. So to be calculated, the percent composition of any element is the mass of that element divided by the mass of the compound multiply 100%. We are assuming, of course, mole, which means when we put the mass of the element, we're going to put the mass of 1 mole of the element, and when we put the mass of the compound, we're going to put the molar mass, which is the mass of 1 mole of that compound. Let's look at the following. If I have this compound here, which is ethanol, and I want to calculate the percentage composition, it means that I want to calculate the percent composition of the carbon element, the hydrogen element, and the oxygen element. To start doing so, let's start with the percent composition of carbon. I need to have the mass of the carbon in the compound. That's what a percent composition of carbon is. However, I have 2 atoms of carbon. So I have 2. Every atom has an atomic mass of 12.01 gram divided by, now I need to know the mass or the molar mass of ethanol, which is 46.07 gram. Now this is here grams of carbon and this is here grams of ethanol. You multiply this by 100% and the percentage composition will be 52.14%. Now, for the next element, which is the percent composition of hydrogen, so we have 6 atoms of hydrogen, so 6 times 1.01 divided again by 46.07. So this is the grams of hydrogen and this is the grams of ethanol, and multiplied by 100%. The answer for that will be 13.15%. Then I have, let's just put the decimal point here. Okay. Then I have the percent composition of oxygen, which is 16 grams of oxygen for every 46.07 grams of ethanol, and multiplied by 100%. The answer for that will be 34.73%. Now notice, if you add up these here, all the percentage together, you do have to, they have to equal 100%. You know, like 52 plus 13, that is like 65 plus almost 35, that is definitely 100% if you add the other fractions. Okay, let's move on. Here is another question that is very interesting and I would like to teach you some skills about it. So the question reads, molecule Y contains 68.7% fluorine. The molar mass of compound Y is 166. How many fluorine atoms are in each molecule Y? So, you know, if you read the question, it might really be overwhelming. So the easiest way in those questions is to understand what is your target, what do you need to really solve. At the end of the day, what they want is how many fluorine atoms are there. Let's just do this. How many fluorine atoms are there for every one Y compound? And the way to do so, I will look at the facts that I have here and what they mean to me. So this is a percentage composition of a fluorine. 68.7% fluorine. Compound Y is 68.7% fluorine. So what does that mean? There are 68.7 grams of a fluorine in every 100 grams of compound Y. They also gave you the molar mass of compound Y. So what does that mean? every 1 mole of compound Y will weigh 166 grams of compound Y. Now I go back, I'm going to actually move the location of this one here so it's clearer to you. So again, I want F over Y. How can I get F over Y from these two facts here? Well, the only one that has a fluorine is the percentage composition. So what I'm going to start to put that up here. So I'm going to say there are 68.7 grams of a fluorine for every 100 grams of Y. Then I'm going to, I want the quantity, which is how many atoms of a fluorine for every molecule of Y. Grams don't help. I have to take them into mole. So for a fluorine, what I will say, 1 mole of a fluorine does have an atomic mass of 19.00 grams of a fluorine. Now, grams of fluorine are canceling out. Now, I can keep mole of fluorine because I want it right here, but I need to get rid of grams of Y. This is what the molar mass will help me. So what I'm going to do, I'm going to say, okay, what I know that for every 166 grams of Y, it will be an equivalent to 1 mole of Y. So now, look at what we have. Grams of Y are canceling out, and now I have mole of a fluorine over mole of Y left. So mole will cancel mole, and now I have an atom of a fluorine for every molecule of Y. Now, because this is number of atoms, it does have to be a whole number. So you run your math, and the answer will be 6 fluorine atoms for every 1 Y molecule. When we look at the type of formulas, we will learn how we can get the chemical formula from the mass percent composition, and vice versa. The mass percent composition can give us a formula. So there are definitions of 2 types of formulas we deal with in chemistry. The first one is an empirical formula, which is the smallest whole number ratio of elements. And there is the molecular formula, which is the exact number of atoms in a substance. This is the true formula. So now, if the molecular formula of water, which is 2 hydrogen atoms for every 1 oxygen atom, then the empirical formula will be 2 hydrogen atoms for every oxygen atom, because that's the simplest ratio between 2 and 1. For glucose, 6-12-6, that is what does exist in reality, which is 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. However, the simplest ratio will be CH2O, because that is the simplest ratio between the element, and that's the empirical formula of glucose. Ozone, 3 atoms of oxygen, the simplest ratio between those will be just 1 atom of oxygen. Dinitrogen tetrahydride, which has 2 atoms of nitrogen for every 4 atoms of hydrogen, the simplest ratio between those will be NH2, which is 1 atom of nitrogen for every 2 atoms of hydrogen. So I hope now the definition of molecular and empirical formula is clear. Now let's see how we can calculate the empirical formula from percent composition. Here is a question. Determine the empirical formula of ascorbic acid, which is vitamin C, that contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. So the first thing I do when I address these questions, I will say, here is what I know. In 100 grams of ascorbic acid, I know that I have 40.92 grams of carbon. Now in a formula, I need a ratio which is between number of atoms. So this is why I need a quantity. I can't take a grams. I have to convert to moles. So I'm going to convert that into moles, and I'm going to say 1 mole of carbon has an atomic mass of 12.01 grams of carbon. When you do this mathematically, your calculator will say that 40.92 divided by 12.01, and you're gonna keep, in this case, 4 sig fig. The answer will be 3.407. Next element that you have is hydrogen. So you're gonna say there are 4.58 grams of hydrogen. You multiply this by 1 mole of hydrogen does weigh 1.008 grams of hydrogen. Now when you mathematically log these numbers in the calculator, the answer will be 4.544 moles of hydrogen, and here moles of carbon. Now the last element left is, we have 54.50 grams of oxygen. My conversion factor will be, for every 1 mole of oxygen, there is a mass of 16.00 grams of oxygen. And when you do this mathematically, and you keep again 4 sig fig, the answer will be 3.406 mole of hydrogen. So now what you have is the following. So I'm going to try to simplify this for you right here, right? Now I know in ascorbic acid, if I'm going to write my formula, when it comes to carbon, I have 3.407. When it comes to hydrogen, I have 4.544, and when it comes to oxygen, I have 3.406. Now you know that we never write formulas like that. We need these numbers to be whole numbers, right? So the way to do this mathematically is you take the smallest number and you divide everything by the smallest number, which happen to be the moles of, I'm sorry, here I'm gonna have to make this correction now. This is here oxygen, sorry for that. Okay, so we have to look at the smallest number and divide by that number, which happens to be moles of oxygen. So you're going to divide this by 3.406, this also by 3.406, and this here by 3.406. Of course, this one will equal 1. This one is almost 1. And when you do the 4.544 divided by 3.406, the answer will be 1.33. So now your formula, the new formula, looks slightly better. So what you have is 1 carbon. When it comes to hydrogen is 1.33, and oxygen is 1. We still don't accept fraction. So now what you start to do, you start to multiply by the next integer, right? So if you multiply by 1, that's useless, but you start multiplying by 2. So I'm going to change the color, and I'm going to start to multiply by 2. If I multiply by 2, then this here will become 2. This here will be 2.66, and this here will be 2. So the new formula now is C2H2.66O2. It's still not working, right? Because I still have fraction. So now the next integer is 3. So with a new color, let's pick the green color here. And if I multiply this by 3, then it's going to equal 3. If I multiply this by 3, then that will be 3.99, which is almost, I can say that's almost 4. And if I multiply this by 3, it's going to be 3. So now my new formula is C3 H4, because 3.99 is so close to be an integer, right? It has to be really close. And O3. And this is here the empirical formula of ascorbic acid. Okay? Now, I'm going to give you a question to practice what you just learned. And these are the steps that you normally follow. Practice calculating the empirical formula from percent composition. This question is now for you to practice. You have to repeat the same process that we went through together. And now, what is the empirical formula of a compound with 40.0% carbon, 6.71% hydrogen, and 53.3% oxygen? I'm going to give you a hint so you know if you did your work correctly. The answer for this question will be the compound formaldehyde. And formaldehyde is the following compound. So the formula is CH2O. Why am I telling you this? You know, if you do everything properly and you receive this answer, it means you have understood it and you can perform this math on your own. Now, you might have seen what we just went through, which is the explanation of how to determine the empirical formula from the mass or the percent mass composition of the element. However, there is also what we call determination of the empirical formula experimentally by performing experiment. So how does that work? Now, here is an example. So I'm going to read it and try to explain the experiment for you. We combusted 11.5 grams of ethanol. And if you remember what combustion is, it is burning a compound in the presence of oxygen for all the carbons to be converted into carbon dioxide and all the hydrogen to be converted into water. We collected 22.0 grams of carbon dioxide and 13.5 grams of water. Now here is the equation that we are dealing with. We know that ethanol has carbon, has hydrogen, and has oxygen, but we don't know what the ratio is. And we know it reacted with oxygen to give me carbon dioxide and water. Clearly, I was able, let's go back to the slide, I was able to know and measure, because this is an experiment here. So I'm going to explain to you a little bit about what you are looking at. This is here we call a water trap. So what does that do? This is your water trap. When you combust ethanol here, the compounds are the products, right? Water and carbon dioxide, they're gonna come out. This is a trap that will be trapping all the water that's coming out, and this is the absorber or the traps for carbon dioxide. So we know their mass before the reaction, and then we can know their mass after the reaction, so we know how much water was absorbed, in another word, produced, and how much carbon dioxide was absorbed, which means how much of it was produced. So if you look at this equation, you know that all the carbon was converted to carbon dioxide and all the hydrogen was converted to water. But I can't say the same about oxygen, and the reason why, I can't say that all the oxygen here came from ethanol, because I also reacted with an external oxygen, so it's hard to tell. So what I'm going to do, I will be able, using stoichiometry, to retract back the carbon and the hydrogen, and then using the math to get information about oxygen. So let me show you how I will start working on this question. I will say, okay, well, I know that we collected 22.0 grams of carbon dioxide. Then what I'm going to do, I'm going to convert that into moles, and I'm going to say, okay, every 1 mole of carbon dioxide has a molar mass of 44.01 grams of carbon dioxide. Now, I can track that into carbon, and I can say every there is 1 mole of carbon for every 1 mole of carbon dioxide, and that came from the formula. Now that's going to give me the moles of carbon, so I can calculate that. And the reason why I want to calculate it, because I definitely will need it to determine the empirical formula. So I'm going to say, okay, I have 22.0 divided by 44.01. Clearly that's equal almost to a half. And I need 3 sig fig in this case. So the answer here will be 0.500 mole of carbon. Okay? Now, I'm going to go and address water. I will say I have 13.5 grams of water molecule. And I'm going to say, okay, I know that 1 mole of water molecule does have or does weigh 18.02 grams of water. Now, also I know there are 2 moles of hydrogen for every 1 mole of water. Please pay attention. This is a very common mistake that students do. Okay, there are 2 moles of hydrogen for every 1 mole of water. Not 1 mole, 2 moles. Now, I will do the math, and the answer for 13.5 divided by 18.02 and multiplied by 2, that will be 1. Again, I need 3 sig fig, so that will be 1.50 mole of hydrogen. Okay, so that's good. I have moles of carbons and moles of hydrogens. Now I need moles of oxygen so I can have the whole empirical formula. However, as I have said, I cannot really track oxygen and claim that all the oxygen here and here came only from ethanol, because some oxygen can also come from the oxygen for combustion. So what will be safer to do, since I know that the 11.5 grams of ethanol has only the XYZ of carbon, hydrogen, and oxygen, I already know the moles of carbon and the moles of hydrogen. If I convert that into mass, because I can say, okay, there is 12.01 grams of carbon for every 1 mole of carbon, then the mass here will be 6.01 grams of carbon. And I can do the same for hydrogen. I can say there is 1.008 grams of hydrogen for every 1 mole of hydrogen. And if I multiply that by 1.008, that will give me 1.51 grams of hydrogen. Now remember, the 11.5 grams are hydrogen, carbon, and the oxygen in ethanol. So if I want to know grams of oxygen in ethanol, all I have to do is, I would say 11.5 grams of ethanol, I'm going to abbreviate ethanol, minus 6.01 grams of carbon, minus 1.51 grams of hydrogen, and the answer here will be 11.5 minus 6.01 minus 1.51. I'm gonna get 3.98 grams of oxygen. To get empirical formula, I need moles, so I'm gonna immediately say 1 mole of oxygen weighs 16.00 gram, and if I do the math, that will give me 0.250 mole of oxygen. So here are the last, or I'm gonna move the answer up here so you guys can see it. So I have 0.250 mole of oxygen. So now I know all the moles of the three elements. I'm gonna have to divide by the smallest. So with a different color, let's divide by the smallest, and the smallest will be the oxygen. If I divide this by 0.250, that's equal 1. If I divide 0.500 moles of carbon by 0.250, that's equal 2. And for hydrogen, if I divide 1.5 over 0.25, then that's equal 6. So now I'm done. For carbon, I have 2. They are all integers, right? They are all whole numbers. For hydrogen, I have 6. And for oxygen, I have 1. And that is the empirical formula of ethanol, that it was calculated experimentally. Okay? Now pay attention to this question. Please go over it more than one time, and make sure that when you work on assignments that you do work on a similar question. Very high chance you will see something like that in your exam. Now, to determine the molecular formula, you know how we just worked on the empirical formula? How do we do that? Empirical formulas, we need the empirical formula and we need the molar mass. So if you want to determine a molecular formula from empirical formula, then you gotta have the empirical formula and you gotta have the molar mass. And what does that mean? Let's see here. Empirical formula is multiplication of the empirical formula will give you the molecular formula. So let me explain to you what does that mean. Remember how I did show you that glucose has the empirical formula of CH2O. That is the empirical formula of a glucose, but it's not the molecular formula. There are 6 empirical formula for every molecular formula of a glucose, which is C6H12O6. So the key to get the molecular formula is to know this number. How many empirical formulas are there in one molecular formula? And to do so, you need to do the following mass. N, which is the number I want to calculate, will equal the molar mass divided by the empirical formula molar mass. So here is a question. What is the molecular formula of a compound with an empirical formula of NO2 and a molar mass between 90 and 95? So what I need to calculate really is N. So here is, let's calculate N. N equals the molar mass. Did they give us the molar mass? Well, they give us the range. So a lot of students will ask me, what am I supposed to use? They didn't give me the exact molar mass. They told me it's somewhere between 90 and 95. The answer, and I'm going to show you how mathematically, doesn't really matter. You can pick either because N has to be a whole number, so you are going to round anyway. If you go to the lower end, you're going to round up. If you're going to the higher end, you're going to round down. So N will equal, let's use 90. 90 divided by, now I need the molar mass of the empirical formula. I need this part. So I have 1 nitrogen and 2 oxygens. Every oxygen is 16. So 16 and 16, that is 32. Nitrogen is 14. So you have 14 and you have 32. 2. So if you add them together, that will be 46. So now if you divide 90 over 46, that will be 1.956 in your calculator, so you are going to say almost 2. If you use 95 over 46, so that your calculator 95 divided by 46, your calculator will tell you that is 2.07, which you will say it's almost 2. So this is why it didn't really matter. So what you know right now, that there are 2 of NO2 in the molecular formula. So your last conclusion will be the molecular formula will be, you're going to multiply this by 2, so it will be N2O4. All right. I hope you enjoyed this lecture, and I will see you in the next one.